All right, so we're going to cover a couple things in this lesson. We are going to go over some new concepts, and we're going to differentiate between what uniform and non-uniform motion is, and then we're going to look at how to measure time intervals. So let's start with this. Here's a diagram, and this is also on your handout as well, so let me skip to the handout because we'll write an answer to it. We'll do it together. So in this diagram, we have a car. And it's the same car, it's just we have a picture of the car at exactly every second. So at time 0, we have the picture of the car here. So let's call this t equals 0. And then at 1 second, and at 2 seconds, and at 3 seconds, and so on. 4, 5, 6, 7. So after exactly 1 second, we get another picture of the car. And we notice the car has changed its position, it's moved. And the question is asking us to describe the motion of the car. So we actually have two things happening. It happens somewhere in the middle. But in the beginning, during the first half, we notice that after every second, so from 0 to 1, the car has moved this much. But then from 1 to 2, it's moved this much. And from 2 to 3, this much. So for every second, the car seems to be covering more and more distance. So we can say here that the speed is increasing. That's just for the first half. For the second half, we notice the opposite happening. Here we're covering a lot of distance during this 1 second, and then less during the next, and even less during the next. So here we can say the speed is decreasing. All right, so getting back to the PowerPoint, here we have a similar example. So a golf ball attached with a light that flashes regularly with time, so maybe every second or every 1/10 of a second, for example, is dropped in a dark room. From shoulder height to floor, let's just say shoulder. Which set of dots representing the flashing light would you observe in a photograph of the ball's downward motion? So basically, it's asking us to describe when you drop something, the motion of it. Now when you drop something, we all know gravity causes things to accelerate, get faster and faster and faster. We will be doing more detail on gravity, but for now, knowing that things get faster, which one of these three images actually looks like something's getting faster? Well, let's analyze them. The middle one looks like all the dots have equal spacing. So that means for every identical time interval, you're covering the same distance. That would sort of mean that the speed's not changing. It's constant. We know that's not true when you drop something. It doesn't move at a constant speed unless it's reached terminal velocity, which is something else we'll talk about later. The first one, however, we're covering a shorter distance, and then a little bit longer, and a little bit longer, and longer, and longer. So we're covering more and more distances for every time interval. That would mean our speed is increasing, which would make sense with a ball falling under gravity's acceleration. But what about C? C seems to say the opposite. It almost looks like as the ball is falling, it's slowing down. We know that's not true. So in this case, we would go with A. Now, when we talk about motion, scientists call the study of motion kinematics. Kinema is actually, I can't remember if it's Latin or Greek, but it's the word for motion. And Hollywood took that word and replaced K with a C, and you have cinema, which is moving pictures, right? Physics kept the K and calls the study of motion kinematics. Okay, and it's a very, very important concept in physics because everything in our entire universe is in motion. Okay, you may be sitting down in front of your computers right now watching me talk about this, but you're not exactly motionless, right? You're on the Earth. The Earth is spinning about its axis and moving around the sun. Right? The sun itself is also moving around a black hole, right? At the center of our universe. Not universe, at the center of our galaxy. And even our galaxy is moving. It's currently on a collision course with Andromeda Galaxy. Not anytime soon, so don't worry about that. But the point is, everything is in motion. And so understanding motion is a very, very important concept in physics. So to understand motion, we need to be able to describe motion. So we have lots of terms to describe motion, and a lot of you are familiar with these terms because we use them every day in English. Things like distance, speed, velocity, acceleration. But there are slight differences with how we use them in physics and how we use them in English. And so we're going to go over some of them today and the rest as we move forward with this unit. All right, so motion, we define motion as the movement of an object from one place to another. Well, that's obvious, but the next part is very important. It says, as measured by an observer. So what does that mean? Right, well, let's look at the first part, movement from one point to another. So you have an object here in this location, and it moves over here to this location. We can call that motion. But it's also important to an observer. So from your point of view, looking on the screen, you can see my pencil move from here to here, and me as well. But what if I move with it? Okay, from your point of view, both myself and the pencil have moved. But from my point of view, the pencil is about 5 centimeters in front of my nose, and even though you might say it's moving, to me, it's still 5 centimeters in front of my nose. So that's another important concept in physics. Okay, the point of view by an observer is extremely important, and physics does not give any preference to one observer over another. So what does that actually mean? It actually means that, again, everything is in motion. Even the school is in motion. In fact, I can move the school. How? It's actually quite simple. All I have to do is go walking outside. That's it. Because then from my point of view, the school's getting, if I'm walking away from the school's getting further away from me. And therefore, according to physics, I can say it's moving. I know it sounds kind of weird, and it sounds like I'm a bit crazy saying that. But, like I said, physics does not prefer any one point of view over another. All the laws of physics will work in all points of views. Right? So let's look at this question. And I think this is also on our handout, so I'm going to switch from the PowerPoint to our handout. This is question number 2. Okay, it says 2 golf carts are traveling at the same speed in the same direction along a straight level path. Are the carts in motion with reference to each other? Explain. And the answer would be no, they're not. And the reason is, just like I said before with the pencil and my nose, right, their position relative to each other remains the same. Now I can give you another example. Imagine you're in the passenger seat of a car. And I'm sure everyone has experienced this. You're in the passenger seat of the car, and the car's on the highway. And you pull up to someone else. Right next to them in the other lane, in the adjacent lane, and now you're moving at the same speed with each other. You can just look over and watch that person driving. Now they might be going 100 kilometers per hour, but from your point of view, they're right there, and their position relative to you is not changing. Right? So from your point of view, they're not moving. Technically, from your point of view, all the trees that are on the side of the road are shooting backwards at 100 kilometers per hour. Okay? So let me pause that mess, because that was... All right, so now we're going to move on. And we're going to look at uniform versus non-uniform motion. Uniform is just a term which means the same, or not changing, or constant. So when we say something's in uniform motion, we mean the motion of that object is unchanging. Now it could be at rest and remaining at rest, or it can be a car on the road moving 60 kilometers per hour and continuing to move 60 kilometers per hour. So both the person at rest and the car moving at 60 kilometers per hour, we can say are undergoing uniform motion. Non-uniform motion, well, non-uniform means not the same or changing. So if that car that was traveling at 60 kilometers per hour has to stop because there's a red light, it comes to a stop. Its motion changed. And that motion going from 60 to 0 in whatever time period is called non-uniform motion. Okay, so let's go over a couple examples. These are on our handout as well. And we're just going to look at whether or not they're uniform and non-uniform. I'll go over the first one with you, and then I'll let you look at the other ones. So part A says a rubber stopper is dropped from your raised hand. So I'll take a ball. It's dropped from your raised hand to the floor. Is that uniform or non-uniform motion? Well, we talked about a little bit of how gravity actually causes objects to accelerate. So it gets faster and faster as it falls. If it's getting faster and faster, its speed is changing. So that would be non-uniform motion. Okay, so I'm going to pause here, and I want you to take a minute or two and look at parts B to D. So just in case you're watching this later, I'll just repeat myself. Non-uniform motion cares both about the amount, so in this case how fast you're moving, and also what direction you're moving in. So even though your speed is staying the same, because your direction is changing, non-uniform. Let me go back to the PowerPoint. All right, measuring time intervals. So time is very important, especially in the study of motion. Right? And in a physics class, when we usually do labs, we still have to figure out how we're going to do that. But there are different ways of doing it. You can use a digital timer, a computer with sensors attached, and something also called ticker tape timers. Maybe the easiest thing for us to do would just be everyone uses their own cell phone. But before, in the past, we've used something called ticker tape timers. So I'll just quickly explain what that is. Here's a picture of it here. This is just carbon paper. So I mean, if you touch it, you'll get like some carbon on your finger. But then right there is a nail that's sort of pointing into the screen. So you can't see the point of the nail. And underneath the carbon paper is what we call ticker tape. It's just long paper. Okay. And what this does, you plug it in, and with electromagnetism, it just attracts and turns it off, and attracts and turns it off, and causes the nail to bang down like this. And every time it hits, it makes a dot on the piece of paper. And it hits at regular intervals. So just like before, when we were studying the position of a car, at regular intervals. If that position became greater for each interval, that meant it was speeding up, and if it became smaller at each interval, that meant it was slowing down. So we could analyze whether or not an object is speeding up or slowing down by attaching this ticker tape to it and having it shoot across the room, and it would make the pattern of dots. Okay, so let's just look at some examples. So in this pattern, this is actually on, these two are on your sheet, so let me just switch back. So in our first pattern, okay, ticker tapes timers will usually do 6 dots for every 0.1 seconds. So there's dot 0, let's just call that our starting point, and then 1, 2, 3, 4, 5, 6. There's 0.1 seconds, and again 0.2 seconds, and again 0.3 seconds. And you'll notice, if you took a ruler to it, the amount of distance that's being covered for every 0.1 seconds isn't changing. So in this case, you can say the motion would be uniform. However, in the next case, again, 6 dots, 6 dots, 6 dots, in this case, in the first 0.1 seconds, that's the distance covered, and then a lot more, and then even more so. So we'd say the speed is increasing. If the speed of increasing, we're supposed to say what type of motion it is, we would say it's non-uniform motion. Okay, so like I said, analyzing a lot of physics problems means we have to use equations, and when we use equations, we're going to have to know how to rearrange them. So let's just try a couple practice problems. Alright, so we're going to have to be able to make sure we're okay with rearranging equations. So let's just try a couple together. So here's one. In math, you'll use x a lot. Don't use x too much in physics, but a big one that we're going to use is t. T represents time. So let's just use t's instead of x's. I find for some reason that throws off a lot of students. A question that they could solve with an x, suddenly they can't solve if it's a t. It's just so ingrained into our minds in math class. Solve for x, solve for x, solve for x. Alright, let's look at this question. So on either side of the equation, we have a term with t, and we need to rearrange and solve for t. So first, what I'd like to do is on each side of the equation, I'd like to collect like terms. So why don't I collect all my terms with a variable t on the left side and with a variable of, well, with no variable on the right, so all of our constants on the right. Now if I have 11t over here, if I want to bring it to the other side of the equation, I have to get rid of it here using the opposite operation. So if this is like a plus 11t, I can subtract 11t here, okay, so that 11t minus 11t is 0, but whatever I do to one side of the equation, I have to do to the other side. So I would subtract 11t from the other side. So now I would have 13t, and again, the order at which you write it doesn't matter. 9 minus 11 is the same as minus 11 plus 9. Don't forget the t, like I just did. And then on the other side of the equation, we have a 5. So now here we have like terms. And so we can subtract them. 13 minus 11 is 2. But we still have this 9 here. We need to bring that constant to the other side. So to do that, since we're adding it here, we'll subtract it from both sides. So 9 minus 9 is 0. It's now gone from the left side of the equation. And on the right side, we have 5 minus 9, which is negative 4. Okay, so now we still have to solve for t. We haven't quite done that because we have 2t. T is being multiplied by 2 now. So to undo that, to undo a multiplication, we divide. But again, you can't just divide it on one side of the equation because that changes the equation. It's no longer true if we did that. So we have to do it to both. So now we're going to have t. The 2 will cancel. 2 divided by 2 is just 1, but we don't have to write 1t, just t by itself. Equals minus 4 over 2 is just negative 2. Okay, I'm going to try another one because I have time. You know what? I'll do one with fractions. Everybody hates fractions. Let's do one with fractions. About 3 over 4t minus 2 equals a half t plus 2. All right, let's do this one. So again, what we have is t's on both sides of our equation, so we need to bring them all to one side of the equation. I usually like to bring them to the left side, but it doesn't really matter. That's just my own habit. Okay, so first thing I can do is there's a couple things you can do to solve this equation. If you want to get rid of the fractions right away, because you hate fractions, what you can do is look at the denominators. We have a 4 and a 2. Okay, and we can multiply by both sides by 4. Right, you look at the greatest common factor, really. So if I multiply both by 4, 4 over 4 cancel. They're gone, right? But here's the tricky part. You can't just multiply both sides of the equation by 4. It has to go into every single term. So if it helps, you could put brackets there so that you know that 4 should go into both terms. Okay, because you have to multiply really everything on both sides of the equation. So over here we're just left with 3t. Great, no more fraction. But we have 4 times minus 2 is minus 8. That's all right, still no fraction. Now over here we have brackets. So as long as we multiply this half by 4, we're also multiplying it by everything in the bracket. Because multiplication, whether you do a times b times c, doesn't matter if you do b times a times c or c times b times a. So these will cancel. 4 divided by 2 is just 2. So we're left with 2 times t plus 2. Okay, that's one way you can sort of approach this problem if you don't like fractions and you want them gone right from the start. And you just look at the denominator, and the easiest way to figure out what number to multiply them by, you could have done 2 times 4, which is 8, and multiplied both sides by 8. That would have also got rid of the fraction, because 8 over 4 is just 2, and 8 over 2 would be 4. That would work. But in our case, this one works better. All right, so let's just leave the left side alone. And on the right side, we're going to expand this. So we're going to use our, if you remember, math class called the distributive property, just like we did up here, and multiply through. So we'll have 2t plus 4. Now it's very similar to the example above. We're going to subtract 2t from both sides, so we'll have 3t minus 2t, okay? And then it's gone from our other side. And we can add 8 to both sides, so on the other side we'll have 8 plus 4. 3t minus 2t is just t, and 8 plus 4 is 12. Okay, so let me just pause there, see how I